同学们，大家好，今天我们来学习施密特正交化。施密特正交化的公式看起来有点复杂，但它要完成的操作却比较简单，就是将非正交积化为正交积。比如 x1、x2 是这个平面里的一组非正交积，经过施密特正交化后，就能得到 v1、v2 这组正交积。下面我们来看看它的具体推导。先从特殊的二维向量空间 R 平方说起。假设下面有两个向量是 R 平方中的一组非正交积，我们将其中一个向量对另一个向量进行投影，操作后就能得到 R 平方的一组正交积。下面来进行代数推导。假设非正交积为 x1、x2，施密特正交化的第一步就是任选其一作为 v1，比如选 x1，这样 v1 就等于 x1。然后做出 x2 在 v1 上的投影 x2 一拔，其垂线向量就是要求的 v2。根据向量减法的几何意义可知 ，v2 等于 x2 减 x2 一拔，而 x2 一拔与 v1 在同一条直线上，因此 x2 一拔等于 k1v1。在这个式子里，只有 k1 还不知道，下面就来求解它。因为 v2 与 v1 正交，所以它们点积为0。将 v2 等于 x2 减 k1v1 代入此式，整理一下，这样就求出了 k1， 从而求出了 R 平方中的一组正交积 v1、v2。需要说明的是，上述推导过程并没有被限制在 R 平方中，它也可以完成在三维空间中的平面上寻找正交积的任务。比如 x1、x2 是三维平面中的一组非正交积，通过施密特正交化方法就能找到该平面的正交积 v1、v2。讲完了二维，下面来看看三维的情况。还是以特殊的三维向量空间 R 立方为例，假设图中的三个向量是 R 立方中的一组非正交积，先按照前面二维的做法，将其中任意两个向量正交化，然后向这两个正交向量所章程的空间做垂线，从而得到第三个正交向量，这样就得到了 R 立方中的一组正交积。思路讲完了，下面开始具体推导。假设非正交积为 x1、x2、x3， 将 x1、x2 用前面的方法将其正交化为 v1、v2。下面将 x3 向平面做投影，得到其投影向量 x3 一拔。x3 与 x3 一拔的连线即为所求的 v3。为了让同学们看得更清楚，这里将图像旋转一下。因为数值的向量是 v3， 根据向量减法的几何意义可知 v3 为 x3 与 x3 一拔之差，也就是 v3 等于 x3 减 x3 一拔。因为 x3 一拔在 v1、v2 所章程的平面上，所以它是 v1、v2 的线性组合，也就是 x3 一拔等于 k1v1 加 k2v2。为了好看，这里再旋转一下图像。从这个角度看， x3 一拔是 v1、v2 的线性组合就很明显了。将 x3 一拔等于 k1v1 加 k2v2 代入第三行，就得到了这个式子。因为 v3 垂直于整个平面，自然也就垂直于 v1、v2。这样我们就得到了 v3 点乘 v1 等于0， v3 点乘 v2 等于0。用刚刚二维中同样的计算方法，我们就能计算出 k1、k2。这部分的具体推导，感兴趣的同学可以查看我们的文字版。将它们带回第三行，这样就求出了 v3。这就是三维中的施密特正交化。将此推广到 n 维，这样就得到了施密特正交化的完整表达。
Professor Dave here. I want to teach you the Gram Schmidt process.
He knows a lot about all kinds of stuff. Professor Dave explains.
In the previous tutorial, we learned all about orthogonal vectors and how we can generate from these a set of orthonormal vectors by taking each vector and dividing it by its length. This makes each vector's length equal to 1, and since they were already orthogonal, the new vectors become orthonormal. But what if we start with a set of vectors that are not already orthogonal? Furthermore, how do we go about making an orthonormal basis for a vector space, given any set of vectors that form a basis. To do this, we need to learn something called the Gram Schmidt process. So let's take a look at this now. To see how this works, let's examine the vectors v1 to vn, which serve as a basis for the vector space V. Our only requirement for these vectors is that they form a basis. We are no longer assuming any orthogonality between them. The Gram-Schmidt process takes these vectors and forms a new orthogonal set of basis vectors, which we will label u1 to un. The process goes as follows. First, start by setting the first new vector u1 equal to the first basis vector v1. For the second step, take the second vector v2 and subtract from it the inner product between v2 and u1, divided by the length of u1 squared times the vector u1. So altogether, that looks like this. Then the third step will be to take the vector v3 and subtract a similar term. The only difference is that now we take the inner product between v3 and u1 in the numerator, and then we also subtract another term, which is the inner product between v3 and u2, divided by the length of u2 squared times u2. At this point, you may notice a pattern emerging. For each new vector, we must subtract an additional term that involves the inner product of the current v vector with each previously found u vector. So we will need one more such term for each vector. The reason we need to do this is that we are subtracting off any part of the v vector that is not orthogonal to the new vectors we have found, leaving only the orthogonal part. To make things a little more succinct, each of these new vectors after the first one can be put into summation notation as follows. uk equals vk minus the sum over I from 1 to k minus 1 of the inner product between vk and ui, divided by the length of ui squared times ui. If this notation is unfamiliar, go back and check out some of my tutorials on sums. Otherwise, we can quickly see how the orthogonal basis we just wrote can be derived from this expression. Some useful tips to help remember how this looks include noting that the only v vector that appears in the formula has the same number as the u that is being found. Also, every other u vector that has already been found will show up in a specific term in the remaining v vectors. Another helpful feature is that u1 has one term in its formula, u2 has two, u3 has three, and so on. For ordinary real vectors, what we mean by inner product is simply the vector dot product. And recall that the length of a vector is simply the square root of its dot product with itself. So just considering this case, we can rewrite these terms with dot products. This might all look a bit overwhelming at first glance, but let's look at an example and take it step by step. Consider the basis vectors for R3. v1 equals 1, negative 1, 1, v2 equals 1, 0, 1, and v3 equals 1, 1, 2. We always start by setting our first vector u1 equal to the first basis vector, so u1 equals 1, negative 1, 1. Now we get to step 2, where we take our second vector v2 and subtract v2.u1 divided by u1.u1 times u1. Well, v2.u1 will be 1 times 1 plus 0 times negative 1 plus 1 times 1, or simply 2. Then u1.u1 will be 1 times 1 plus negative 1 times negative 1 plus 1 times 1, or 3. So u2 equals 1, 0, 1 minus 2/3 times 1, negative 1, 1. Simplifying this expression, we get u2 equals 1/3, 2/3, 1/3. Finally, for the third vector, u3, we will take v3 minus v3.u1 over u1.u1 times u1 minus v3.u2 over u2.u2 times u2. Now simplifying, v3.u1 is 1 times 1 plus 1 times negative 1 plus 2 times 1, which is 2. We already know that u1.u1 is 3, so let's just use that. Then v3.u2 is 1 times 1/3 plus 1 times 2/3 plus 2 times 1/3, which equals 5/3. And then u2.u2 is 1/3 times 1/3 plus 2/3 times 2/3 plus 1/3 times 1/3, which becomes 1/9 plus 4/9 plus 1/9. This is 6/9, which simplifies to 2/3. Plugging in all these dot products, we get u3 equals 1, 1, 2, minus 2/3 times 1, negative 1, 1, minus 5/3 over 2/3, which simplifies to 5/2, times 1/3, 2/3, 1/3. Lastly, going through the vector addition, we end up with u3 equals negative 1/2, 0, 1/2. These three vectors form an orthogonal basis. Now, if we wanted an orthonormal basis, as we know, we would take each of these resultant vectors and do what we have already learned, dividing each vector by its length, thus creating a new set of vectors of length 1. And since they are already orthogonal, these vectors will be orthonormal. To be thorough, let's go ahead and do this for the three vectors we just found. u1 equals 1, negative 1, 1, u2 equals 1/3, 2/3, 1/3, and u3 equals negative 1/2, 0, 1/2. We know that u1.u1 equals 3, so the length of u1 is root 3. We also saw that u2.u2 was 2/3, so the length of u2 is root 2/3. We must still calculate u3.u3, which ends up being negative 1/2 times negative 1/2 plus 0 times 0 plus 1/2 times 1/2, which equals 1/2. So the length of u3 is root 1/2. Now taking u1 and dividing by its length, we get 1 over root 3, negative 1 over root 3, 1 over root 3. Taking u2 and dividing by its length, we get 1 over root 6, 2 over root 6, 1 over root 6. Finally, dividing u3 by its length, we get negative root 2 over 2, 0, root 2 over 2. These are the orthonormal basis vectors we obtain from our original basis, thanks to the Gram-Schmidt process. Being able to generate an orthonormal basis is a useful tool, as the bases themselves can be very helpful for certain calculations. This process also works for different kinds of vector spaces, such as ones involving functions. It just changes how we compute the inner product. Now that we've gone over the process of finding an orthonormal basis from any existing basis vectors, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.